Now in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD equals to 3 units in its length. Inside this rectangle ABCD we have those two semicircles. The radius of this big semicircle is 2, the radius of this small semicircle is 1. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles are all right angles. So already known. So this is a right angle. This is a right angle. This is a right angle. This is angle ABC. This is also a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle. This point is point P. We will define the center of this small semicircle. This point is point Q. We will define the tangent point of those two semicircles. This point is point S. Likewise, we will define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we will define the point of tendency of tangent AE. This tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction. That is to say, we will extend line segment AE and side DC by side line until they touch each other. So here, this is their touching point. We will define this point as point F. DC is one side of rectangle. Again, DC is one side of rectangle ABCD, and therefore it is absolutely a straight line. Then we extended the straight line DC by straight line, and the result is DF. When you extend a straight line by straight line, the result must be a straight line. Therefore, DF is also a straight line. So if we focus on the upper side of this straight line, DF at point C here, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equals to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So by doing this construction, we created here the small triangle ECF. We will define this angle EFC as alpha. So in the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So this missing angle must be equal to 90 degrees on alpha. We have the radius PL of this big semicircle. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever your radius that is drawn to the point of tendency, you can implement rule 1. So I'm going to click here on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have also the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So I can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius PL that is equal to 2. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle. The radius QG is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So inside this small right triangle GQF, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. It is very easy to see that PD is the radius of this big semicircle, that is 2. PS also, it is also the radius of this big semicircle, that is 2. So PD equals to 2. PS also equals to 2. QS is the radius of this small semicircle, that is equals to 1. QC is also the radius of this small semicircle, that is equal to 1. And finally, CF is the missing line segment, so we define the length of the missing line segment CF as x. In the next step, we will prove that the big right triangle LPF, this big right triangle LPF, is similar to this small right triangle, triangle GQF. So we will prove that those two right triangles are similar to each other. So I write it now. So we will prove that the big right triangle LPF is similar to this small right triangle, triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles they are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PLF. In the big right triangle LPF, and it is equal to this angle, that is actually angle QGF. In the small right triangle GQF. And again, we actually found out that angle PLF in the big right triangle LPF equals to angle GQF in the small right triangle GQF. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to angle alpha, as it belongs to the small right triangle GQF, it will be defined as angle GFQ. So again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle LPF. In the big right triangle LFP, and it is equal to this angle, that is actually angle GQF. In the small right triangle GFQ. So if it again, we actually found out that angle LPF in the big right triangle LPF equals to angle GQF. In the small right triangle GQF, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the triangles inside this big right triangle LPF are correspondingly equal to all the triangles inside this small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it now. We actually found out that the big right triangle LPF is similar, this is the sign of similar, to the small right triangle GQF, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP, the big right triangle LPF, over side GQ in the small right triangle GFQ, equals to side PF in the big right triangle LFP, over side QF in the small right triangle GFQ. And put again, we actually found out that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP equals to 2. It is the radius of the big semicircle that is equals to 2 over GQ. GQ is the radius of the small semicircle that is 1. And it is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus x. Again, PF in total equals to 4 plus x. Over QF. QF in total equals to 1 plus x. So in conclusion, we should find out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And finally, we get that two times 1 plus x equals to 4 plus x. So here we'll open the brackets on this side of the equation, and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, and we get that in this side of the equation we have 2x plus x is x, so in total in this side of the equation we have x plus 2, that equals to x minus x is 0, so in this side of the equation we left only with 4. Here we subtract 2 from this equation, and finally we get that x equals to 4 minus 2, that is 2. So actually found out that the length of this line segment CF is equals to x is equals to 2 units. In the next step, we'll prove that the big right triangle ADF is similar to this small right triangle ECF. So at the note, we'll prove that the big right triangle ADF is similar to this small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, and therefore they are equal to each other. So actually this is angle ADF. In the big right triangle ADF, and it is equal to this angle. This is actually angle ECF. This one right triangle EFC. So I'll repeat again. We actually found out that angle ADF in the big right triangle ADF equals to angle ECF in the small right triangle EFC. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha. Angle alpha is a common angle that belongs to both triangles, so you can write down that the angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the big right triangle ADF, it will be defined as angle AFC. And angle alpha equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle AFC, it will be defined as angle EFC. So again, this equation means that angle alpha equals to itself. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle DAF. in the big right triangle AFD, and it is equal to this angle, that is actually angle CEF. In the small right triangle EFC. So I repeat again, if we found out that angle DAF in the big right triangle AFD equals to angle CEF in the small right triangle ECF, they are both equal to 90 degrees minus 1 part, therefore they are equal to each other. So if we prove that all the figures inside the big right triangle ADF are correspondingly equal to all the figures inside this small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So if it down, if we found out that the big right triangle ADF is similar, this is the sign of similar to the small right triangle ECF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AD, the big right triangle ADF, over side EC in the small right triangle EFC, equals to side DF in the big right triangle ADF, over side CF in the small right triangle EFC. Repeat again. We derive that side AD, the big triangle, over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3 over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is 2. So in total DF equals to 6 plus 2, that is 8. Again, DF in total equals to 8 over CF. CF equals to 2. So if we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. And therefore, if we found out that 3 over EC equals to 4. Here we multiply this equation by EC, and we get that 3 equals to 4 times EC. Here we divide this equation by 4. And finally, we get that the missing side EC is equals to either 3/4 or 0.75 units. So actually, this is the missing side EC, that is equals to either 3/4 or 0.75 units. What is the length of the missing line segment BE? But before that, we'll find out the length of side BC. What is the length of side BC of rectangle ABCD? We have the rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. but AD is 3, therefore BC must be also equal to 3 units in its length. So I already know that we found out that side BC equals to 3 units in its length. What is the length of this missing 9 segment? 9 segment BE. From the domain, it is very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So I write it down. I should found out that BE equals to BC minus CE. So BE equals to BC. BC is 3 minus CE. We just right now found out that C equals to 0.75. So in total, BE equals to 3 minus 0.75. 3 minus 0.75 is 2.25. So if I found out that the missing 97 BE is equals to 2.25 units in its length. What is the length of side AB of rectangle ABCD? Repeat again. What is the length of this side AB of rectangle ABCD? You know, according to the same rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side DC must be equal to the opposite side AB. But DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC in total equals to 6, and therefore the opposite side AB must be also equal to 6 units in its length. Side AB equals to 6 units in its length. So in the next step, I'll copy the right green triangle ABE in a new page, and we'll implement the Pythagoras theorem on this right green triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. Side AB equals to 6 units in its length, and side B equals to 2.25 units. So actually, this is the green right triangle ABE that according to the original drawing. According to the Pythagoras theorem, in this green triangle, in this right triangle ABE, AE squared equals to AB squared plus BE squared. So repeat again, AE squared equals to AB squared plus BE squared. So I write it down. AE squared, this is the square of the hypotenuse, equals to AB squared plus BE squared. AE is the missing side, so we leave it as it is. AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36. Plus BE squared. BE is 2.25, and therefore BE squared is 2.25 squared. That is equals to 5.0625. So in total, AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. Here we take a root out of this equation, and finally we get that the missing 97AE, this is actually also the opposite AE, is equals to the square root of 41.0625. The square root of 41.0625 is equals to 4.608 units. In conclusion, we shall find out that the length of the missing 97AE is equals to 4.608 units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the length of this 97AE. So in the domain, we have a rectangle ABCD. We know that side AD of this rectangle equals to 3 units in its length. In addition, inside this rectangle, we have those two semicircles. The radius of this big semicircle is 2, the radius of this small semicircle is 1. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside the rectangle are right angles. So those 4 angles are all right angles. In the next step, we define the relevant points to this question with letters. We define the center of this big semicircle, this point as point P. We define the center of this small semicircle, this point as point Q. We define the touching point of those two semicircles, this point is point S. In addition, we define the point of tendency of tangent AE with this big semicircle, this point is point L, and finally we define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did the construction. That is to say, we extended line segment AE and the side DC by a straight line until they touch each other. This is their touching point. We defined the touching point as point F. DC is one side of rectangle ABCD, therefore it is absolutely a straight line. Then we extended the straight line DC by straight line, and the result is DF. When you extend the straight line by straight line, the result must be a straight line. Therefore, DF must be also a straight line. So if we focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees. According to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle, plus this missing angle. In total, it must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we focus on this small right triangle ECF. In this small right triangle ECF, we define this angle EFC as alpha. So we continue to focus on this small right triangle ECF. In this small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big right triangle, triangle ADF. In the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Here, dP equals to PS, the above the area of the circle is equals to 2 units. Here we have also SQ equals to QC equals to 1. It is the radius of this small semicircle, it is 1. And finally we have line segment CF. The length of line segment CF is unknown, so we define the length of this line segment CF as x. So here we have PL is the radius of this big semicircle. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG. The radius QG that is equals to 1. The radius QG is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the sum rule, rule 1. So in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the triangles inside this big right triangle LPF are correspondingly equal to all the triangles of this small right triangle GQF. And therefore those two right triangles are similar to each other according to angle similarity rule. So again, actually found out that the big right triangle LPF is similar, this is the sign of similar to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP, the big triangle, over side GQ, the small triangle, equals to side PF in the big triangle over side QF in the small triangle. Okay, again. We derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of this big semicircle, that is 2, over GQ. GQ is the radius of this small semicircle, that is 1. And it is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus x. Again, PF in total equals to 4 plus x over QF. QF in total equals to 1 plus x. So in conclusion, we found out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation, and finally found out that 2 times 1 is 2, so in total on this side of the equation we have 2 plus 2x equals to 4 plus x. Here we subtracted x from this equation, and finally found out in this side of the equation we have 2x minus x is x, so in total we have this side of the equation x plus 2, that is equals to x minus x is 0, so in this side of the equation we have to only be 4. So in conclusion, we found out that x plus 2 equals to 4. Here we subtracted 2 from this equation, and finally found out that x equals to 4 minus 2, that is 2. So we found out that the missing 97 CF is equals to x, that is equals to 2 units in its length. In the next step, we proved that the big right triangle ADF is similar to this small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself, it's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the triangles inside this big right triangle ADF are correspondingly equal to all the triangles inside this small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I said again, we actually found out that the big right triangle ADF is similar to the small right triangle ECF according to angle similarity rule. And from the fact that the big right triangle is similar to the small right triangle, we derive that the following relationship exists between their sides. We derive that side AD of the big triangle over side EC of the small triangle is equal to side DF of the big triangle over side CF of the small triangle. And for the again, we derive that side AD of the big triangle over side EC of the small triangle equals to side DF of the big triangle over side CF of the small triangle. AD equals to 3 over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2, 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is 2. So in total, DF equals to 6 plus 2, that is 8. So again, DF in total equals to 8 units, and CF equals to 2. So in total, we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so we found out in conclusion that 3 over EC equals to 4. Here we multiply this equation by EC, and finally found out that 3 equals to 4 times EC. Here we divided this equation by 4, and finally found out that the missing side EC equals to either 3/4 or 0.75 units. And again, we found out that the missing side CF equals to the missing side CE equals to either 3/4 or 0.75. What is the length of side BC of rectangle ABCD? Repeat again, what is the length of side BC of this rectangle ABCD? We have the rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But AD equals to 3, therefore BC must be also equal to 3 units in its length. So we know that BC equals to 3, EC equals to 0.75. Therefore, the missing side BE must be equal to BC minus EC. Again, BE equals to BC minus EC. BC is 3, EC is 0.75, and therefore in total BE equals to 3 minus 0.75, that is 2.25. In conclusion, we found out that missing side BE is equals to 2.25 units in its length. We use again the same rule that said that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But DC in total equals to 2 plus 2, that is 4, plus 1, that is 2. So in total, DC equals to 4 plus 2, that is 6. So DC equals to 6, therefore the opposite side AB must be also equal to 6 units in its length. In the next step, I copied the right green triangle ABE in a new page and implemented the Pythagoras theorem in this right green triangle, triangle ABE. Side AB equals to 6 units in its length, side B equals to 2.25 units, and the length of the hypotenuse AE is unknown. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In this right triangle ABE, the hypotenuse is AE, and therefore the square of the hypotenuse is AE squared, and AE squared must be equal to AB squared plus BE squared. AE is the missing side, so we leave it as it is. So AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is 5.0625. So in total, we actually found out that AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. In conclusion, we found out that AE squared equals to 41.0625. Here we took out of this equation and finally found out that the missing 970 AE, the 970 that we are looking for, is equal to the square root of 41.0625. The square root of 41.0625 is equal to 4.608 units. So in conclusion, we found out the length of line segment AE is equal to 4.608 units. Okay, thank you very much.